This is Chapter 7, Problem 3, a worked out example. The information in your book can be summarized in this sentence. The question being asked is, do individuals who have seen political ads about a certain topic score differently than the general population? We are told that the general population has a mean score of 40, and that's the number of answers correct on the test they took about this particular issue. And the sample that have watched this political ad scored 48, 41, 40, 51, 50. So let's begin by getting the information we know we're going to need, which is we know we're going to need N. We know we're going to need the sample mean. We know we're going to need the sum of squares. And we know we're going to need the variance for that sample. And there's a few more things we're going to need, but we'll wait till we get there. So first off, we know our N equals 5. Let's calculate our mean. Of course, we know the formula for mean equals X equals the sum of all X's divided by N. And so let's sum these up, equals the sum of 48, 41, 40, 51, and 50, which equals would have been quicker to just do it in my head very quickly, which equals 230. 230 divided by 5, which equals 46. We know that we're going to need to know the sum of squares in order to estimate the standard deviation of the population. And so we know the sum of squares is simply the sum of each score minus the mean squared. And let's figure those out. So that equals the sum of 48. I say 48 because that's the first value, minus, and I say 46 because that's the mean, squared, plus, and I don't need to have both the sum sign and the plus, so I'm going to erase the sum sign there, plus the next value is 41 minus 46 squared, plus, and the next value is 40, 40 minus 46 squared, plus, and the next value is 51, 51 minus 46 squared, plus, and the last value is 50, 50 minus 46 squared. And if we sum all of those up, let's take it a step further, equals 2 squared plus negative 5 squared plus negative 6 squared plus 5 squared plus 4 squared. And if we calculate this through, we get 4 plus negative 5 squared is 25, negative 6 squared is 36, 5 squared is 25, 4 squared is 16, and the sum of squares in this problem equals 106. So let's fill that in. And let's fill in the mean, 46. And to continue on and calculate the variance for the population and the standard deviation for the population, we would continue on, and this is the only thing that's different when we're using the t value when we're estimating is right here. And this is the only difference that we use. And normally when we calculate the variance for the distribution, the variance, excuse me, we simply take, normally we just have the variance equals the sum of squares divided by n. But in this case, because we're estimating it, we're not using this formula. We are going to use sum of squares divided by degrees of freedom. And what is degrees of freedom? It is sum of squares divided by n minus 1. And so degrees of freedom is always n, well, at least always in t-tests, n minus 1. So we can do that problem fairly easily. We know that our sum of squares is 106. We can divide by our n, which is 5, minus 1, equals 106 divided by 4. And that is equal to 26.5. So let's fill that in. And if we wanted to calculate on and find the standard deviation for this distribution, we would simply take the square root of the variance, and that equals the square root of 26.5, and that equals 5.115. We won't really be using this information, but it puts it all into context. All right, now we're ready to go on. And let's do the solving of this problem. So, step 1, let's define our populations and state our hypotheses. Our population 1, the research population of interest, is people like those who have seen the political ad. And population 2, people in general who have who have not seen that political ad. We know that our research hypothesis is simply asking whether population 1 scores differently from population 2. So we're looking to see whether the mean scores for population 1 are different, not equal to the mean scores for population 2. And that is our, let me make this a little more clear, that is our research hypothesis. That's what the researcher is interested in. And we know that our null hypothesis simply states that the mean for population 1 is equal to the mean for population 2. So moving on to step 2, we define our comparison population. And we know that our comparison population is for the general population, the distribution of means with an estimated spread. So let's go on then and figure out what this means. So first of all, the mean for our population we're given in this case And in this case, the mean, the number that the average person got correct, is 40. To make it clear what we're talking about, it's 40 answers correct. We don't have to write that here, but it helps to keep it in mind. That's what we're comparing it to. We know that we are assuming that the population is normal, so the shape is normal. And we need to be told that, but for all of the problems in our chapters, we are assuming a normal distribution. Normally, typically, we'd have to have an n greater than 30 to make that assumption. But in this case, we are told that this is normal. And the spread, in this case, is going to be the estimated standard deviation for the distribution of means. Now, we've already estimated the standard deviation for the population of individuals. So to figure out the standard deviation for the distribution of means, we simply take standard deviation for the distribution of means is the square root of the variance for the population divided by n. You might be asking, why aren't we doing degrees of freedom here? And the reason is because we have already estimated. We did that when we figured out the standard deviation for the population of individuals. The only time we need to use that degrees of freedom is when we are estimating, and we only estimate one time. So we have already estimated, so now everything else will use n. And when you say I've already estimated, I mean that when we calculated the standard deviation, when we took the sum of squares, we divided by degrees of freedom, and that was our estimate. So to figure this out, we simply need to have the square root of, and we already calculated out our variance. So let's go back up and find it. Our variance in this case was 26.5. 26.5, and we're dividing by n now, which is 5. So now we have the square root of 26.5, which is, now we take 26.5 divided by 5, and to get our variance for the distribution of means, and that equals 5.3. And now we take the square root of 5.3, and that equals 2.30. So what does all this actually mean? So first off, we let's draw this in this little picture that we like to see. First off, we had the population of individuals. From that, we drew a sample. I'm not making a precise description of our sample, but from our sample, we had a mean of 46. And we inferred about the distribution of means from this sample. And we infer that our distribution of means has 46 excuse me, we don't assume that it had a mean of 46. We assume its distribution. So we assume that our distribution of means has, like the population, a mean of 40, but a standard deviation of 2.3. So what that means is we have our regular lines of standard deviation. So here is our raw scores of 40 and 2.3 is the standard deviation. So Next, we will have 42.3 plus another 2.3 gives us 44.6. And we would do the same subtracting. We know that that equals to z-scores. The 40 is equal to t-scores of 0, 1, 1, and 2. And so we are comparing our sample mean to see where does it fall in here. And that is what we're basically doing with those little pictures. We are looking for a difference. We're not looking for a one-tailed test. We're looking at a two-tailed test. So we're going to look to see if our value is either in the low tail or in the high tail. So if it falls in either of those locations, it will be significant, but we have to find out what the cut point is. And so our next step, step 3, we're going to determine cut point. And we do that by looking at the table on page 677. And when we look at that table, we're going to be looking for a two-tailed test using alpha equals 0.05, and we'll be looking up for the value of 4 degrees of freedom. So let's pull that chart up. And I do have it here for you. So if we expand this so we can actually see it, we see how the columns are laid out. The one-tailed test is here on the top. So here we're looking at one-tailed test. Degrees of freedom, here's our 4 degrees of freedom, and we're looking for 0.05. So we find out that our cutoff point is, and we look for a two-tailed test because that's what we're doing here, and degrees of freedom 4 and cutoff point 0.05, and we find out that our cutoff point is 2.776. And so our cutoff point, or our critical value, is plus or minus 2.776. And that means that we're looking for a cutoff value of minus 2.776 or plus 2.776. And so if our value falls greater than 2.776 or less than minus 2.76, we get to reject the null hypothesis. So what is our value? To calculate this, we need to, this is basically like calculating a z-score, but we're calculating a t-score. And we have to place our sample t-score on the chart. And our sample t-score is just our sample mean minus our population mean divided by the standard deviation for the distribution of means. So that equals 46 minus 40 divided by 2.3. And if we run that calculation through, we find out that that equals 2.61. And now we have to make a decision. we know that we need to have, in order to reject HO, we have to place our value where it falls, and it needs to be less than minus 0.2776 or greater than 2.76. Our value is actually 2.61. 2.61 is not less than minus 2.776. 2.61 is not greater than 2.776. So it's not to the extreme of either of these cutoff points. And so in this case, we fail to reject HO. And we fail to reject HO because our value of 2.6 fell right about here. 2.6. And because it did not fall in either green area, we fail to reject HO, and we conclude, based on this standard, that individuals who saw the political ad did not score differently on a knowledge test than the general population. And we would actually, we would end up putting the t-score in there. We would put the t-score and the degrees of freedom. And we'd put what the score was, 2.61. And then we put not significant, period. So if I were advising this researcher, I would say, you know, really, this was not significant, but if you got a larger sample, you could probably find a better result. So I would encourage this researcher to get a larger sample in the future, even though at this point, based on this very small sample, she did not get a significant result. Thanks for tuning in.